Good afternoon to those in the UK and buenos dias to those in Mexico. Thank you for joining us for this, our fourth session of this section for this section of the Binational Seminary between UNAM and Manchester Met University. Today, Dr. Nushin Karimian will be your host. She will chair the session. I am Magda Giordano, the Academic Secretary for Enes Juriquilla, and thank you very much for joining us. Dr. Karimian.
Thank you very much. Buenos dias to our colleagues in Mexico, and good afternoon to everyone who has joined us from UK. It's a very sunny Manchester here. It's not very likely to get a sun in Manchester, but it's a good start. I'm happy to welcome our first speaker, Mr. Segun Popula. Mr. Segun Popula received his BTech degree in Electronic and Electrical Engineering from the Ladok Akitola University of Technology in Nigeria, and the MH degree in Information and Communication Engineering from the Department of Electrical and Information Engineering from the Covenant University in Nigeria. He's currently pursuing a PhD degree at the School of Engineering, Faculty of Science and Engineering in Manchester Metropolitan University here in the UK. He was a lecturer with the Department of Electrical and Information in Covenant University. His research interests include wireless communications, machine deep learning, cybersecurity, and the Internet of Things. He has published research papers in reputable peer-reviewed journals and conference proceedings, including the IEEE Internet of Things Journal, IEEE Access, Neurocomputing, Elsevier, Wireless Personal Communications, Springer, Cogent Engineering, Taylor and Francis, amongst others. He also serves as a reviewer for top journals and conferences. He is a registered engineer with the Council for the Regulation of Engineering in Nigeria. So without further ado, I would like to pass on to our invited speaker, Mr. Segun Popula. Thank you.
Okay, thank you very much, Dr. Nushin. And it's my pleasure to be here. Thank you. Can I confirm that you can all see my slide?
Yes, we can.
All right, thank you very much. So my name is Segun Popula, and like I've been introduced, I'm doing my PhD in the Department of Engineering, Manchester Metropolitan University. And I'm at the end of my second year. The title of my presentation this afternoon here in the UK and morning over there is Federated Deep Learning for Botnet Attack Detection in Critical Infrastructure. Okay. Now, looking at critical infrastructure in the UK, according to the Center for the Protection of National Infrastructure, national infrastructure are those facilities, systems, sites, information, people, network, and processes that are necessary for a country to function and upon which daily activities depend. So those are national critical infrastructure. And according to that body, which is the Center for the Protection of National Infrastructure, they coin out 13 sectors that are under this category, which include the chemicals, civil, nuclear, communications, defense, emergency services, energy, finance, food, government, health, space, transport, and water. So these are critical infrastructure because the citizen depends on this infrastructure. But of late, we discovered that the technology has advanced, and there's this, apart from the traditional internet, we now have the Internet of Things, whereby things like machines, like traffic lights, like sensors, smart sensors in health sector, that is fixed on maybe aged people or can now communicate directly with other devices. And now we have intercommunication, not just you and I communicating together, but we have devices and machine empowered to communicate with each other via the internet. That is the Internet of Things. But the problem we have here is that there has not been standardization of this technology enough because it is cheap, that is low cost. Now that has led to, and its adoption is growing faster in diverse application areas. So there are different security vulnerabilities in this technology. And because they are using national critical infrastructure, that exposed those infrastructure to cyber attacks. And to back that up, recently we've seen smart grids in the US, in other parts of the world, being attacked by cyber terrorists. In the future, the war of the future will no longer be fought by guns. The war of the future will be fought using the internet, and we must try to secure the infrastructure. Imagine if smart grid, the national grid of electricity in the UK shut down. Lives will be affected, means of livelihood, trains will be grounded, and that's the consequence. So one major form of that attack is IoT botnet attack. So people leverage the security vulnerability in IoT devices and recruit a lot of them that are scattered, distributed across different geographical locations, and use them to form a network of bots. And that you can also call zombies, so that you mobilize them like soldiers to attack a particular infrastructure. And that has happened. And that happened in 2016, and it shut down critical services like Netflix, like CNN and others. So that's the consequence of cyber attacks. Now, different ways by which these attacks has been mitigated. We have authentication, access control and other things. But the ones that we are looking at currently, that I'm looking at in my PhD, is the application of machine learning and deep learning. So the difference between, if you look at this, the image at the bottom is showing the architecture of machine learning and deep learning. So you see the difference between them is just the depth of the hidden layer. So the diagram, the image at the right-hand side is just showing the architecture of how cyber attacks happens using the Internet of Things. So I need to move now to the next slide. So we try to, as in any other meaningful research, you do your literature review and related works. And we discover that the state-of-art deep learning methods fall into 4 different categories: centralized deep learning, localized deep learning, distributed deep learning, and federated deep learning. But what we discover is that centralized deep learning, localized deep learning, and distributed deep learning, they violate the privacy of data, because there's no machine learning without aggregation, without data. You have to learn from the pattern of data. And when you are doing that, you don't want to breach the data privacy of the users. And looking at the example of GDPR that is now in place in European Union now, it has a lot of consequence if you breach that. So federated learning is just a method of applying deep learning without breaching the data privacy of users. So we've adopted the methods, the previous method, centralized deep learning, and the published papers are listed here. We've published in 3 outlets. And concerning federated learning, we try to review the state-of-the-art works, and those are the ones in the table that I have at the right-hand side. We have 10 major ones, but the research gap there is that they've not considered IoT traffic in their data set. And also, they are not looking particularly into botnet attack scenarios. And also, there's what we call zero-day scenarios, attack that has never happened before. How do you detect that if it's happened for the first time? So those are the things that informed the research we are now doing. These are the aim, and the objective is to develop federated deep learning method for zero-day botnet detection in IoT edge devices. And these are the objectives of this research. So we try to set up, because IoT, Internet of Things, is a network of distributed devices. So we try to experiment with 5 different devices and then train the model locally and aggregate the model in a cloud server. So by doing that, the data that is private to individual user is not leaving their devices, because in conventional machine learning, you have to aggregate that data onto the cloud. So if you are taking data from my device and storing on cloud, anything can happen along the way of transmission. And even in the cloud, the privacy of data can be intruded. So you can use that kind of application in health scenario when privacy is very, very important. So we try to do this and see if we can achieve deep learning without accessing the data of the individual. So this is the algorithm that was used. And these are the hyperparameters. So we try to structure our data set in this way to ensure that there are unique. If you look at ED1, DDoS attack did not have any sample before. So we want to ensure that we are able to detect attack that has not happened before, even if they are happening first time, so that we don't leave anything to chance. So we try to simulate these using Python programming language and Sklearn and other deep learning framework, and we achieved this result. We saw that from this graph, after the 5 communication rounds, the accuracy, the precision, the recall, and the F1 score, which are the metrics for measuring your effectiveness of your model, are very high, because the higher, the better, and they are in percentages. So we got this result, then we compared it, our result, with the other method, the centralized deep learning, localized deep learning, distributed deep learning. And we saw that it has a very good performance compared to CDL, but without breaching the data privacy of individuals. Centralized, we breach the data privacy. So that's the advantage. Other ones are lower in performance. So this is the training. So the side effect of this method is that it involves the training time. The time to train this model is higher. That's the cost of doing that. So we have to have a trade-off. Do you want to protect privacy, or you want to spend more time training your model? So, and also against CDL, the memory space required is lesser. So that's another advantage. Then to conclude, these are just in summary using tables. We try to compare in terms of data aggregation. FDL does not need data aggregation. That's why it's good for cases whereby you want to protect users' privacy. And these are just what we find out at the end of our research. And this is where I'm doing my PhD. I acknowledge MMU and Saretech, who is a company that is sponsoring this PhD. These are the references that are cited in the. Thank you for listening. So I'm done. Yeah.
Thanks very much. That was a great presentation. Are there any questions?
We don't have any questions on the chat, but I had one. When you say that this model can be trained without accessing the data, the private data, then what kind of information does it use? How do you teach it? If you don't have any, what kind of, you have to get some data, not the private data, but some data.
Yeah, you're correct. If you want to train a model to perform a task, you have to train it with a data set that is gotten from that scenario. Yeah. What I mean, let me just clarify that. What I mean is that the data will be accessed, but the model training, instead, the conventional machine learning is that you aggregate the data from different sources and then combine them in a centralized place, which is in the cloud. So you have access to data of different people. But we are saying, no, you are not going to send your data to me. I'll bring my model to you, train it on your device, then I will live with the model without living with your data.
I see.
Does that
I
answer
see.
your question?
Yeah. It makes it very clear. So it goes, learns, and then goes away, but it doesn't take it. It's like you don't put it all in, just to use a very simple example, in the same Excel sheet. I mean, you don't download it into one. You just go. Oh, great. That sounds very good.
Correct.
Yeah. Thank you very much.
You're welcome.
Thank you very much. That's a great presentation. Thanks very much for also the good question. It's always great to ask good questions, as I'm sure it will be beneficial for everyone. Great. If there are no questions on our YouTube and on Facebook, we can move on to our next speaker. Is that okay? Yeah. Okay, great. So, our next speaker is Mrs. Saeed Adil. Saeed Adil is a doctoral researcher. He's working with World Rugby to improve the regulations for body padding using material testing and finite element modeling. He holds an undergraduate degree in mechatronics engineering from SRM University and an MSc in sports engineering from Sheffield Hallam University. He has worked as a design engineer and a sport engineer researching into hockey, tennis, and now rugby. So again, thank you very much for accepting our invitation. And without further ado, I would like to pass on to our second invited speaker.
Hi, everyone. I hope you can hear me and see my slides as well.
Yes, we do. Thank you.
Thank you for the introduction, Ashleen. My research is into modeling padded clothing that's used in rugby and updating the regulations for them. So, the process started off by looking at the Regulation 12, which governs the body padding that is allowed in the sport of rugby. Now, if you look at the regulations in rugby, we critique the literature and the regulation that is existing, and we found 3 areas of concern. That's the padding area, the density, and the impact testing. Now, we'll go through each one of them. So the padding area, in the regulation, there is a certified area where padding is allowed. That's on the left-hand side of my screen. Well, the regulation states padding can only be on the shoulder area and not anywhere else. But there are loopholes in the regulation text which allow manufacturers to put padding all over the jersey without even having to meet any impact criteria. So that was one of the first areas we found that was concerning. The other thing is the density criteria. Now, if you read the regulation states the density of the material used for padding has to be under 60 kilograms per meter cube. Now, if you look at the padding, it's usually not uniform. It's sometimes hexagonally structured, which has different padding thicknesses all throughout the cross section, sometimes triangular. They use these shapes because it helps fit better on a shoulder joint or across the body. And sometimes you find varied geometry across the padding, which makes it harder to test for density. So beyond that, the third thing we found that was a concern was the impact testing. Now, the impact test set up in the regulation defines a steel plate dropping onto a steel anvil, and you place the padding in the middle to check if it does not offer too much protection. Now, it is not, you'd never find a steel-on-steel impact during a rugby game. So it is a little bit unrealistic. It is repeatable, but unrealistic. And the shoulder padding that is there is only allowed to reduce risk of cuts and lacerations. again, a flat impact between two steel objects will not replicate a cut or a laceration that may occur. So based on our findings, the area of concern, we did some testing. The first thing we looked at was compliance versus density. Now, we carried out simple compliance testing where we compressed the padding using two flat plates to look at how compliant the material is or how soft or stiff the material might be. And then we carried out some density testing by cutting out paddings from the given padding we have. And you expect to get, uniform circular cylindrical structures, which you could calculate the weight, the mass and the volume and get the density of. But in reality, you get structures which are warped cylinders, and measuring them leads to error in density calculations, and higher error in measuring the final density of the material. Our findings from this study showed that density as a regulatory material property is quite variable or erroneous. You only test the material, not the final product, and usually our foams are stuck between two layers of fabric, and it does not provide any meaningful information. Whereas compliance, on the other hand, is quite straightforward. You can write a program on a universal test machine and it would do the test for you. You test the final product, the material and the fabric in combination as to what a player would wear during the game, and it complements the impact testing. So one is a low-speed compression test, one is a high-speed impact test. So we published this, and it is an open access paper in the sports engineering conference. One of the other things we did was develop a biofidelic impact test. Now, the impact test that is there, steel on steel, not very realistic. This project is working in combination with a researcher at the University of Sheffield. Now, Angus developed a test bed which is mimicking the shoulder area, a rigid core with a muscle layer and a skin layer on top. And we carried out some stud impact testing to mimic what would actually happen if a human skin comes in contact with the stud, which is usually worn in the game of rugby. So we carried out some impact testing, and I'm just showing the video of a perpendicular impact, but we did impacts at different angles as well. Now, using this data, we were able to carry out some FE simulations. So the simulations we did was based on the muscle and skin simulant, which Angus developed. We did some material testing, built our different material model, and then carried out some testing with the stud coming down to see what would happen, and introduced element deletion criteria to mimic the injury that would occur on the human skin tissue. So again, FE simulations are an easier way of simulating such injuries, because we'd never get ethics for testing out on humans and impacting them with stuff to see how their skin reacts. So we've validated this model against our impact testing at different angles, and we've been able to run simulations. So let's say we can introduce foam paddings of different properties and see how the skin would tear if we use the soft, or if we use the stiff or a rigid padding, how the force dissipates. Not only that, we were able to simulate different impacts. So, someone stamping on a player and pulling the leg back would result in a skin tear. So the ability of FE, again, is once you've validated the model, you can mimic different scenarios. And using this model, you can test out different scenarios of impact or different padding, which might be soft or rigid, and figure out, if this should be allowed or this should be regulated or not. So those simulations and the data from all our testing was being fed back to World Rugby to help improve the Regulation 12. So we, throughout our research, we have been working with World Rugby and the manufacturers to keep them in the loop of what we're doing, what we're suggesting, and what changes we might bring in the near future, all to improve and ensure the safety and reducing the risk of injuries such as cuts and lacerations in the game of rugby. But our RFE model has more applications. Well, it can be used to study different sport where there is interaction between the human skin and other objects such as a ball or sporting equipment that may be, or understanding the interaction between the human body and the turf. There have been reports about how the synthetic turf has led to more skin injuries when players dive or come into contact with it, or looking at the human anatomy and how the skin would change under different scenarios, or even at the medical industry, so looking at different surgical operations or any interaction between equipment and the human skin, and you could simulate those interactions basically. So that's a small view into my research. I would like to thank all the technicians at ManMet for their continued support, all the manufacturers who have provided samples for us to help us carry out this testing, and above all to World Rugby for funding this research. Thank you very much for your time. If you have any questions, I'm happy to answer them.
Thank you very much. That was a really interesting talk, very short and sweet, as they say. Very interesting, and I believe that your work will continue progressing, and we do definitely look forward to hearing more about your work in the future. Are there any questions from our participants here?
Yeah, I had a question for Adil regarding we had a talk from Manchester before about, I think, prostheses and the use of these, materials. And,
Auxiliary liners.
Yeah, I think.
Yeah, that's my professor, Tom Allen. Yes.
So I was wondering, so it is related. I mean, what you learn from the padding in these particular interactions can be useful for the development of new prosthetic devices?
Yes, it can be used for checking how the prosthesis devices interacts with the human skin, and what different shapes would do to the human skin. Yes, it is all transferable.
Mm-hmm. And I had one question, if before I let you go, before I stop, how does the development of these new materials feeds into the regulations in rugby? Will they, for example, if you demonstrate that a certain material is not, it's not protective, can you feed this information to them and then they can change the regulation? But how long does it take? And are you thinking of, is that what's going to happen?
Well, they haven't changed the regulation in a long time, so that's why this research is happening. So the contradictory part about the regulation that is in rugby is the padding shouldn't offer too much protection. So in every other sport, you're aiming for more protection, but the regulation here limits the amount of protection you can provide. So yes, anything that we are simulating right now is being fed back to World Rugby and the manufacturers to be like, this is where we're going to set limits. This is what would be allowed, or this is what will not be allowed. But then everything that comes into the regulation would undergo a trial period to see what the effects are on the game and on the manufacturer. So we're getting feedback from the regulatory authority as well as the manufacturers all the way throughout.
Got it.
So,
Thank you.
so this FE model will inform World Rugby as well, but it can be used by the manufacturers to see if the padding they're designing, is it, going above the limitations that we're going to propose.
Thank you. That's great. We've got one question in the chat. Do the materials you develop, is it patented or will it be?
So we don't develop the materials. We develop the FE model that can be used to analyze the materials. So our development was the skin model, the muscle, the biofidelic testbed, and the FE model that can mimic it, and that can be used to analyze any material. We don't develop materials to reduce the risk of injuries.
That's great. Thank you. Two more questions for you. Very interesting topic. We've got a question on how accurate is the deleting element functions?
Well, this is one thing we are going for. So we used a skin which has a certain tear rating. Now, again, skin can vary between person to person, depending on gender, depending on age. But then what we're using is a chamois leather to mimic the human skin, and we're validating against that. So we've validated it against the synthetic chamois leather, and it is a close match. We have to use different properties for different impact setup. But again, this model, the way the regulation works, the model will be used to check if it's reducing the risk of injury, not completely stopping it. So if you use the same element deletion setup without padding and with padding, it should give you the ability to test if the padding is reducing the risk of injury or not.
That's great, thank you. And there's another question that says, does it have applications in bicycling and swimming?
It could do in bicycling if, well, it would involve falling off the bike maybe, and then testing if what extent of injury you could get. It possibly could have an application in swimming. I don't, there's not an idea that comes right at the top of my head, but if anyone has ideas, do feel to send it out. So it'll be fun to see where all it can be applied. Sure.
Thank you. And we've got a comment from Jesus saying we have a research project in the development of adjustable sockets. And so I guess that there will be some for further collaborations on the background between you guys. So
happy to.
Thank you very much.
Happy to, and hopefully I can visit Mexico one day and not just see it from afar.
That's great. Thank you very much.
Thank you for having me. Thank you.
Thank you. We have, sorry, I'll just continue. I've just received a comment now, a further comment. So this is from the same person that says we will prepare a proposal for you and LOFRA researchers in order to explore the possibility for collaboration. He obtained his PhD from LOFRA, so I guess that he will be contacting you with regards to that. That's great. Thank you very much. It's great to see that there will be fruitful collaboration output from these talks, and that's exactly the purpose of these seminars and conferences. Excellent. Thanks again, once again, for your very interesting work. We will move on to our third speaker, Dr. Criseyda Ruiz Aguilar. She's an assistant professor at the Escuela Nacional de Estudios Superiores Jericila and is responsible for Bachelor of Technology. She graduated from Instituto Tecnológico de Morelia as a material engineer. She obtained her master's degree in metallurgy and material sciences and doctorate in sciences in metallurgy and material sciences at the University of Morelia, and receiving an honorable mention. She did a postdoc stay at the Instituto de Investigaciones en Materiales, that is part of the National University of Mexico. Dr. Ruiz has more than 7 years of experience in ceramic biomaterials with applications in the regeneration of trabecular and cortical bones, chemical synthesis, mechanosynthesis, powder metallurgy, foaming of polymers, use of porogens and 3D printing. In addition, she's worked in the manufacturing and physical, chemical, mechanical, and in vitro characterization of resorbable ceramic prosthetists, including the synthesis and characterization of bone cements from the recycling of food industry products. Other areas of interest to her are nanomaterials, self-arranged honeycomb structures, and multi-layer films with applications in electronics. She has several international publications. She's also part of the National Systems of Research in Mexico. Great to meet you and great to have you here, Doctor. And so without further ado, I would like to pass on the stage to you. Thank you.
Thank you for the introduction. Do you see my screen?
Yes, we can.
Thank you. Well, good morning. Thanks again for the introduction. Today I'm going to talk about the topic entitled Biotic Calcium Phosphate Materials Applied to Bone Tissue Engineering. First, it's important to understand what a biomaterial is and its main aspect that must be considered for an adequate interaction of the host tissue. According to the definition given by the American National Institute of Health, a biomaterial is any substance, a combination of substances, drugs, natural or synthetic origin, used for a period which replace totally or partially any tissue, organ, or function of the body, promoting individual quality of life. Within the concept of the biomaterial, several stages can be considered or included, which are important to carry out the biomaterials development and each group of biomaterial characteristics. Consequently, they can be biometals, biopolymers, bioceramics, and biocomposites. Each group has unique properties according to the chemical structure, physical, mechanical, and structural properties. In this talk, I'm going to focus on bioceramics because they have the similar characteristics to the bone tissue. And then I want to continue to development bioceramics process, and in the first stage consists of the synthesis or manufacture of this material. In this stage, all the physical, mechanical, chemical, and structural aspects of the bioceramics need to be most similar to the bone tissue to be implanted and to ensure a proper interaction. After all, the in vitro stage with and without salts, it's studied to understand the biomaterial interaction in simulated body fluids, without salts and with cells. On the other hand, with cells, in this case, fibroblasts and osteoclasts allow us to understand the biological aspect as bioactivity, osteoconductivity, osteoinductivity, as well as the dissolution rate, the effectiveness, and the inflammatory response that the biomaterial may present. The in vivo stage permits us to study the bioceramics with animal models. It's important to indicate that according to the application, the animal model is chosen and is need to perform to corresponding tests and then evaluate the biomaterial under dynamic conditions at different periods. As I expressed previously, the bioceramics, like the rest of biomaterials, must compete with and without vitro and in vitro aspect are mandatory to evaluate pH, biodegradability, cytotoxicity, sensibilization, carcinogenicity. All of these are directly related to the bioactivity of the biomaterial, and the in vitro and the in vivo and without cells, as well as the interaction with bone osteoblastic cells can be synthesized the phase or the mineral phase of the bone tissue, among and many other aspects. So it's important to express or to indicate that the bioceramics can be classified into three large groups according to the interaction of the body of the person who contains them. The first group is the bioceramics, which form a fibrous layer that separates the host tissue biomaterial. A couple in love in a long-distance relationship would represent a trivial example of this group. On the other hand, the biomaterials are those bioceramics that form chemical bonds between the biomaterial and the host tissue. This process is named osteointegration, and the name will be, an example will be in a couple in love who always stay in contact direct as a serial example. Finally, the inert bioceramics are materials that can interact with the host tissue under certain conditions, but when they are not formed or they are not interact with chemical bonds, something like a couple in a free relationship. And continue with the trivial examples. The bioceramics that I'm going to talk about are biomaterials. There is important to indicate that the bioceramics can be found in three presentations, like you can see in this slide: natural, synthetic, and nano-size origin. In biomaterials of natural origin, there are polymers and hydroxyapatite that come from the bone matrix. On the other hand, synthetics are the four groups which I mentioned previously: ceramics, metals, polymers, and composites. In addition, to be in a subgroup is a hydrogels. However, it can be classified in the group of the polymers. The nano-size bioceramics are natural or synthetic origin. However, they can be in these two different parts, like origin, natural or synthetic, but bioceramics are the biomaterials that I continue central point. Some different types of calcium phosphate, like hydroxyapatite, beta-3-calcium phosphate, bicalcium phosphate, tetracalcium phosphate, and biotic classes are osteoconductive, which means that there are bioceramics that allow the stimulation and the osteogenesis cells on surface of the structures, wall, pores structures, resulting in a formation of a new tissue. Subsequently, you can see in this video the bone regeneration process, having as a main actors the osteoblast, which are the cells that allow new bone tissue to regenerate, and secondly, the osteoclast, which are the cells that allow to reabsorb the bone tissue. Therefore, the osteoblast can deposit new bone tissue. There are other aspects to consider, which are the bone regeneration, in this case of the process of the bone regeneration in pore structure, such as femur, tibia, fibula, since a wide distribution pores must be complete with that allow the vascularization of the implant carry out. There are a variety of methods of the synthesis and manufacturing bioceramics. However, considering the sustainable aspect as well as the cost benefit, the following synthesis methods are mechanical milling, milk quenching technique, and salt kiln. All of these methods have the particularity that are easy to perform, cheap, sustainable, with a high yield of the biomaterial. On the other hand, the manufacturing of the metals as origin etching, powder technology, and polymer forming are technologies that allow performing bone implants with a precise finishing tailored to every necessary to each people who require it. The synthesis and manufacturing methods previously indicated are techniques that I have worked to the synthesis and calcium phosphate bioceramics and manufacture of the phosphate-based bioactive classes. These two large groups of bioceramics have been successful in the use of medical applications. Some commercial applications are in toothpaste, dental fillings, metal prosthesis coatings in calcium phosphate. On the other hand, the bioactive classes have the characteristic that they are amorphous, but when they come in contact with the body fluids, they crystallize, stimulating the formation of bone tissue. Their commercial application with a greater importance has been in porous scaffolds for endoprothesis application to trabecular bone. Other crucial aspect is the bioceramics characterization. These techniques allows to analyze the chemical composition, the physical properties like morphology, roughness, porosity, and structure. These techniques are emission scanning electron microscope, X-ray diffraction, infrared spectrometry using the Fourier transform, testing machine, and microtomography. On the other hand, the techniques used for in vitro evaluation are body fluid simulation or pH, measurements, field emission scanning electron microscopy, Raman microscopy, calcium and phosphorus radio using energy dispersity or EDS, X-ray diffraction, plasma mass spectrometry, cell proliferation or MTT. On the in vitro stage or the in vitro permit us to study the bioceramics with animal models, as I expressed previously, and it's important to specify that according to the application, the animal model is chosen to perform the corresponding test and evaluate the biomaterial under dynamic conditions at different periods of time. It's critical to denote that another techniques can be used for a characterization. Nevertheless, the techniques mentioned previously are the most used to characterize the bioceramics from the chemical, physical, structural, and mechanical and in vitro characterization. Then I'm going to show some results of my research lines about the calcium phosphate and bioactive classes. In this article was made a comparison between a salt-gel mechanosynthesis techniques to synthesize beta-3 calcium phosphate, and the results obtained in this investigation allow to understand the effect of the synthesis method and the particle size of the tricalcium phosphate powders. To conclude, the salt-gel particles were lower than the mechanosynthesis, as you can see in this slide. And then the method permit us to understand the condition of the milling time under the revolution per minute are variables that affect directly the particles of the tricalcium phosphate. Furthermore, the field emission electron microscope salt-gel powders morphologies show spherical shapes, as you can see, concerning the mechanosynthesis due to the grinding generating agglomerates with irregular form. Then the X-ray diffraction verified the crystalline phase formation. This diffractogram corroborates the formation of the beta-3 calcium phosphate due to the chemical reagents reaction in the solid state process. The calcium and the phosphorus radio in atomic percent was corroborated by EDS. These powders radio values show from 1.4 to 1.8. This data indicates that the calcium phosphate, which allows to analysis and understand the dissolution of the powders in contact with body fluids. Some studies have presented bioactive classes doping with different elements and improve mechanical properties and reduces the dissolution process. Nevertheless, several compositions were manufactured of the bioactive bioglasses doped with zirconia or zirconium oxide to improve the dissolution properties and the cell interaction in this investigation. This slide shows part of the article results, which illustrated the glasses amorphousness and the irregular glass polders morphology. These images obtained by a scanning electron microscope, the last image show how the diffraction pattern with the tetragonal and crystalline structure was. The zirconia interact a nucleating agent, helping to the glass crystallization. Then the bioactive glass powders were obtained and mixed with beta-tricalcium phosphate. Powders in variable amounts with different reagent, forming reagents ratios until obtain scaffolds with a wide pore size distribution. So bone regeneration could occur in long bones, such as tibia, femur, or fibula. They were having a wide pore size distribution and interconnect porosity. This aspect allowed to resorbability, cell proliferation, vascularization, and a better control of the scaffold dissolution to be carried out. For the porosity analysis, 2D cuts were made using X-ray microtomography of the scaffolds, and then a 3D model reconstruction was made, as you can see in this video, which allowed to obtain the percent of the porosity variably from 49 to 52%. The range of the porosity is a consequence of the wide pore size distribution. The in vitro part, the scaffolds evaluation carried out with most fibroblasts to analyze the viability, the cell viability, showing a greater increase in the cell viability in amorphous or in a porous scaffolds than in the control sample. Then I want to continue to show you this article that is a continuation of the previous article. The scaffold present a cauliflower-like morphology, which is characteristic to the mineral phase of the bone tissue. As you can see in these images, hydroxyapatite can show various morphologies depending on the synthesis method and the body fluid in which the biomaterial is in contact. The stimulated body fluid of the SBF affects the dissolution of the scaffolds and release calcium and phosphorus ions due to the local saturation. This phenomenon generates nucleation and hydroxyapatite precipitation. The higher the saturation, the higher apatite formation will be, and the lower the saturation, the hydroxyapatite formation will be inhibited. This analysis of the pH variations as a function of the immersion time in the SBF or simulated body fluid allows to know the behavior of the medium and the scaffold dissolutions due to the hydrogen ions release, permit to know the acidity effect, and the alkalinity occurs in the medium due to the amount of calcium ions are released. It's important to comment that the hydroxyapatite formation occurs in pH values between 6.6 to 7.8. The pH also allows to analyze the cellular metabolism. It prevents tumor formation of the cell's death. And then continues with the in vitro part. The scaffold were evaluated in vitro with MG63 osteoblasts. The cell adhesion and the effect of the porosity of the scaffold is analyzed, and the sample with the higher zirconia content accelerates the proliferation, adhesion, and differentiation of the osteoblasts, resulting in a better osteoconduction and osteoinduction. Then I'm going to show this on scaffold production using porogens. In this study, the tricalcium phosphate scaffolds production using sodium chloride spacer was used to obtain porosity results similar to the 4 cortical bones. then obtain values of porosity of the 63% to 87%. Then continues with the scaffolds were evaluated and in vitro using artificial saliva to be used in dental applications. The hydroxyapatite precipitation was occurred after 14 days of immersion in saliva artificial. In this study, on the other hand, the scaffold were manufacturing using two types of different commercial sugar. As you can see in this slide, you can show the different images of the two brands, different Mexican brands, Sulca and Genuino, with the objective to with different sugar biteable amounts, obtaining different structure with close porous structures, which can be used for cortical bones, such as vertebrae, skulls, and phalange applications. Finally, I want to conclude by saying that I am still studying and completing the in vitro and the in vivo test evaluations. I continue to synthesize and manufacture new and innovative biotic classes, and I continue to improve about the applications of the bone tissue engineering. And I want to say thank you to all the co-authors and students who participate in the different research. Thank you.
Thank you very much. That's once again another very interesting topic. Very good research. It's always great to see that there are so many good researches taking place around the world, and we're very pleased to hear them. We're very pleased to see that there are some connections happening already from these presentations. And so having said that, got no question from YouTube at the moment. Do we have any question from the participants here?
I had a question, if I may.
Of course, thank you.
What I gather from your talk, Dr. Rees, is that you want the material to become part of the, for example, part of the bone tissue, for example, not to stay there, but to contribute to its healing and then disappear, or you want it to stay. I mean, or it depends. Possibly if you're using it for, I'm thinking about filling for teeth, you know, then you don't want it to go away. You want it to stay, to become part of the tooth. But in other cases, you might want the material just to help heal and then disappear. Is that the case?
Yes, well, all my lines of research, they have the main objective that just a period of time and then disappear completely or reabsorbed by the body who contains them. But other applications are like a coatings in metal processes, just to accept and evit to reject the processes. So it's depends of the application and depends of the characteristics of the bone tissue in this case, because some part of the application or dense bones like spools and vertebrae, so dense, don't have porosity inside of them, but long bones like tibia, femur, or fibula, they need to interconnect porosity because you need to into the fluids of the body and need to go out all these parts that don't need to the body.
Yeah, I understand. To have adequate blood supply, for example. You don't want something to block the blood supply in a bone, no? In a long bone, for example. So I see, I understand. Thank you very much.
Thank you.
Thank you. That's great. Do we have any other question? We'll just give it one more minute. There may be people typing. Okay, right. There seems to be no questions. I would like to once again thank you and the rest of our speakers who contributed to our very, very nice day today. And I'm sure we all learned a lot today, and there are some really interesting connections already built, which I'm very proud of. And that's all from me. Hi, Eric. Would you like to add anything?
Yes, hi everyone. First of all, thank you very much for coming for this webinar, and it's a privilege to work with UNAM in Mexico, and I hope we can do much more together. So thank you very much for your time today, and thank you, Nushin, for sharing this. Thank you.
Thank you for organizing such great conference and seminar. It's great. If there is no other comments or suggestions or anything from our colleagues in Mexico?
Well, just to say goodbye, goodbye for now, and we will see you, I hope, soon. Araida Hidalgo has a very nice plan for the summer, so I think we will continue to be in touch. And thank you very much for this opportunity to get to know your university and know your research. It's been very, very interesting for all of us, and we hope that we can, someday, little by little, start building bridges.
Hopefully,
definitely,
yes.
Definitely.
Definitely, that's very, very good speech. Thank you very much to yourself and all our colleagues in Mexico. Yes, it's a pleasure for us to also be presenting and collaborating with everyone at your university. And we look forward to further collaboration from both sides. Thank you all. Have a lovely day, and bye for now.
Bye-bye.
Okay,
Bye-bye.
Thank you. Bye.
Yeah, bye.